All right, everybody. Tonight is the last installment of the different types of chemical reactions that we're going to be learning. Before we begin, you need to make sure that you have your foldable, your purple sheet, and your gold sheets with you. The first one we're going to look at for tonight is synthesis reactions. Synthesis reactions are a type of redox reaction. Electrons get transferred. It's kind of easy to see this because when you have two elements combined, typically there's an electron transfer of some sort. Even if a covalent bond is formed, most likely it's polar, meaning that the electrons are still hovering a little closer to one of the elements over the other. The general equation for a synthesis reaction is A plus B yields AB. Let's take a look at a chemical equation that we could use for real. Sodium metal and chlorine gas, remember Brinkelhoff, combine to produce sodium chloride, which is tasty salt, which is a solid, most definitely. When we balance this out, we need 2 sodium chlorides because of our 2 chlorines, which means we need 2 sodiums as our reactants in order to be balanced. Make sure you write this down on your synthesis reactions tab before you move on. Single displacement reactions we looked at last night. In a single displacement reaction, a single element displaces an element that's already involved in a compound. The single element must be more active in order for the reaction to go. You need to use the back side of your gold sheet in order to complete these. You should have a reactivity series and list of potentials on the back side of your periodic table. If not, I'll show you tomorrow in class. However, in order to know if the element is more active, on your activity series, which is on the back side of your gold sheet, the replacing element, meaning the single element, must be below the element it's trying to replace. I'll show you with the example here. The general equation is A plus BC yields AC plus B. Let's take a look at a real-life example. If we take aluminum metal and we add it to iron oxide, iron 3 oxide, these are solids. We obviously have to do some heating of some sort here. Typically magnesium is used as an ignition source. You light the magnesium and then this goes. The aluminum comes in and it knocks iron out. If you look on the back side of your gold sheet, you'll see that aluminum is below iron 3 on this potential list, excuse me. Because aluminum is lower, it's actually more active. If aluminum had been higher than the iron 3 ion, then this reaction would be a no-go. So we would write no reaction. But because aluminum is in fact lower on your potential list, your electric potential list, aluminum does knock out the iron. Aluminum and oxygen react together to form aluminum oxide. You do have to crisscross your products. So aluminum is a +3, oxygen is a -2. So your final product here is aluminum Al2O3, which is a solid, and then poor iron is left all to itself. It gets kicked out. When we balance this out, we need 2 aluminums because of the 2 aluminums in aluminum oxide. And we need 2 irons in the product side because of the 2 irons in the iron 3 oxide. Decomposition reactions at first glance look very simple. You have a single reactant, it breaks apart into smaller products. You know you have decomposition because there's only one reactant. However, you have 4 different kinds of decomposition reactions that you have to be mindful of. This is what you need to do. write down the definition of decomp on your decomp tab. You may also include the following, that just AB breaks apart into A plus B as a general equation. But then we have 4 types. So I want you to lift up your decomposition and your combustion tabs. And remember those 4 tabs that you cut? We cut the page into quarters. Here's where these 4 decomposition reactions go. Please take a moment, copy down each one, go in the order of elemental, carbonate, chlorate, and then hydroxide. Get all of this written down on your tabs, and then we'll talk about them. All right, let's take a look. Elemental decomposition reactions are the easiest ones to work on, okay? I'm going to slide the chlorate over. Oops, no, I'm not. I'm going to slide the chlorate over, and let's take a look at elemental. So this is where a compound breaks up into its constituent elements. So AB literally breaks up into A and B. An example here is water. Water can be electrocuted under a process called electrolysis, and it breaks down into hydrogen and oxygen gas. Of course, you have to remember Brinkelhoff. Hydrogen and oxygen gas are both diatomic when they're in their elemental form. Then you balance and you're done. That's elemental. That one's the easy one, like I said. Oh, no, not that one. Chlorate goes over here. Let's take a look at the carbonate one. A carbonate decomposition. This is where knowing your polyatomic ions makes life easier. Carbonate is CO3 with a -2 charge. When a metal carbonate breaks down, it breaks down into the following 2 products. We form a metal oxide that you have to crisscross the charges on, and carbon dioxide gas. So here's an example. Calcium carbonate will break down upon heating into a calcium oxide and carbon dioxide gas. Please keep in mind that CaO is only CaO because calcium is a +2 and oxygen is a -2. When you crisscross those charges, it becomes 1-to-1. All right, let's take a look at the chlorate. Again, knowing your polyatomic ions is extremely helpful here. Chlorate is ClO3 -1 charge. When you have a metal chlorate that breaks apart, it breaks apart into the metal chloride and oxygen gas. So here we have sodium chlorate. It breaks apart into sodium chloride and oxygen gas. You do have to balance your equation out. The sodium and the chlorine, when you crisscross those charges, are 1-to-1. Sodium is a +1 charge, chlorine is a -1 charge. When you crisscross that, you get NaCl. We're not just smashing our elements together here, guys, okay? You have to crisscross the charges for each product. Finally, hydroxide. Let's take a look at hydroxide. Hydroxide, again, is a polyatomic ion, OH -1. Your metal hydroxide will break apart into the metal oxide and water vapor. Here we have calcium hydroxide. We heat up calcium hydroxide, and calcium oxide is produced along with water. Notice hydroxide and carbonate are extremely close. They both produce a metal oxide. The difference is when a carbonate breaks down, carbon dioxide is produced, and when a hydroxide breaks down, water is produced. You have to commit these to memory because it's not good enough to recognize that you have a decomposition reaction. You also need to know what kind of decomposition reaction you're working with. Be very mindful of that as you study. Last type, everybody. Here we have combustion reactions. Combustion reactions are special redox reactions. The reason why they're special is that there are no metals here. However, electrons are still transferred in the entire process of a combustion reaction. We all love combustion reactions because these are the reactions for fire. Fire is released, energy is released in all combustion reactions. Heat is always released. Things get very hot in a combustion reaction. That is an exothermic process. A combustion reaction is a carbon-containing compound that reacts with oxygen gas to produce carbon dioxide and water vapor. Notice we don't talk about the heat or the energy here. That's because heat is a form of energy. It's not a true product. The general equation looks like this. Cx, x can represent either an H of some sort or an HO combination, okay? So compound Cx, whatever x represents here, reacts with oxygen to produce carbon dioxide and water. So what does a real example look like? Let's take a look. Gas grills are very popular today. Lots of people own them. And you have to buy propane gas in order to work your gas grill. Propane gas is this compound, C3H8. This is propane gas, okay? And when you light it to start your fire, the propane gas mixes and reacts with oxygen from the air, and together they produce carbon dioxide, gas, and water vapor. It's so funny, not funny, haha, it's more funny, ironic, that water vapor is produced from fire when we use water a lot of times to put out a fire. Here's what you need to know. You have a carbon-containing compound reacting with oxygen. On the beginning here, it looks kind of like it could be a single displacement reaction, but because of that carbon-containing compound and because the single element is oxygen, we then know and can identify this as a combustion reaction, knowing full well that the only two products are carbon dioxide and water. We do have to balance out our equation, so as we do that, we put a 3 in front of the carbon dioxide because of the 3 carbons in propane. We have 8 hydrogens in propane, so we have to put a 4 in front of the water to get our 8 hydrogens. We now have 10 oxygens on the product side, and so we put a 5 coefficient in front of the oxygen on the reactant side in order to balance out our oxygens. Please make sure that you have written everything on your tabs in your foldable from this lecture. You need to have all of these notes as proof that you watched this video. Your notes are now complete. It is now a tool to study so that you learn all these different types of chemical reactions because you are held responsible for knowing all of these. Have a wonderful evening.